On?
Now it's starting recording. It wasn't recording before.
Really?
Yeah.
Oh, okay. Yeah.
You need to start the virtual camera and then the virtual camera is just for the Discord channel so they can see that video. And then you need to start recording and then afterwards we need
What is that? That's a camera. The quality is quite low.
okay. It's because it's compressed through Discord.
Because like in online
That's
class,
why
in online class actually the code or something is
Pardon?
like in the online class actually the code is like very good.
Okay. That's why I always cast my screen as well over the window.
Because during the last week or yeah, I have a picture. Uh, and the quality for the screen is quite.
Okay, I'm sure that's true, but that's why I share always my screen on Discord as well, plus the link to it, so you can actually look at the original Jupyter.
Just go into the link.
Yeah, that's why I post the link. Okay, so on Saturday we have the makeup class for the 10/10 Monday holiday. In the makeup class, I didn't cover any new material per se, but we did some JavaScript OpenCV JS programming, just showcasing that indeed you can run OpenCV now with very good performance in your browser. And basically, the code looks a lot like what you would write in Python. It has the advantage that you can then serve it as a web app, which means that anybody on an iPad, an iPhone, an Android phone, an Android tablet, a Windows, Mac, or Linux machine, or a Nintendo Switch, because they also have a browser built in, and the camera can actually use your application. So that makes it probably the most versatile software distribution method channel. And that's not the end of it. The web technology has been progressing dramatically. Web GPU now allows you even to run, but only on Mac hardware. But Web GPU at the moment, they're working on adding support for the other ones. Web GPU allows you to run Llama or some of the large language models locally on your laptop, also in the browser, which is truly impressive given that these are 7 GB models, neural network models that you're running in Chrome or Firefox, or actually Chrome primarily. But today we're going to look at, last time we talked about color and color predicates, color detection methods, block detection. And I basically just said that color is really tricky, even though it looks very, it looks like it should be very simple to just recognize a red shirt or a yellow shirt some of the students wear. To actually do that in practice if you can control the lighting, is no problem. Then you can make the lighting nice and smooth and uniform, and your color response is going to be very stable. But if you're dealing with a natural scene, outdoors, even indoors, where lights are opening, where spectators are walking in front of your robot casting shadows, then it's basically a hopeless task. Certainly, even if you just think about recognizing an orange ball or something like that. So maybe we'll do that as an exercise at the end of the class today. But if we don't use color, then what else can we use in order to understand the world around us, in order to be able to do object detection and object tracking, for example. If you want to play soccer with your robot, you need to detect the ball, you need to know where the ball is, and you also need to know something about the trajectory of the ball, because if it's rolling, you need to kick it. You need to first walk to the right place, then you need to kick it at the right time. So this object detection and tracking is crucially important for many different applications. If we can't use color, then what can we use? Shape, yes. That's right. So how do we get the shape? Let's say, what do you want to track? A rubber duck. Maybe I can use DALL-E. So DALL-E is a large language model based on diffusion, not a large language model, it's a diffusion model, and you can type in a text prompt and you get a picture back. Oh. Benson, what's your phone number? Just sign up. I'll cancel you out.
No, the zero. No, zero. The 9.
Wait, I'll better turn this off. Otherwise, everybody knows. Then just come and type it. Otherwise, everybody knows your phone number. You get all these spam calls. Should get a code. Okay. Okay, thanks. So let's say I want the yellow rubber duck. In Taipei, sure. Why not? You're out of credit. What? I only
You want me just.
just started. You used to be able to just. Oh no. Okay, never mind. Uh, that didn't work. So if I have something like this, rubber ducks, you may know about Ducktown, which is yes, and there's this. Yeah, this is not going to work. Okay, so now we're trying to detect the rubber duck, right? And even though it's bright yellow, you think you can track yellow, may not be such a good choice if there's clouds moving over. Now we're looking at the shape. In order to be able to identify the shape of something, right? What do I need? Like I can detect the rubber duck shape in this picture quite easily, right? But if I have the upload image, no, just cut and paste. So, if I want to detect the rubber duck in this image, then what? Hmm? The yellow rubber duck.
Just use a color.
Huh?
Just use a color.
No, I mean the duck is in there. It's the same, I just filled the image. It's, you can just think of it as this image, except I filled it with yellow. So it's not quite correct. I would need to actually draw something. So here I want to detect the duck, right? That's easy enough. But now, if I paint this all in yellow here, then it'll be impossible to detect your duck, right? Because all you have left at that point will be the two eyes. Can I make this larger? Okay, now I'm a little bit too aggressive, but it's pretty clear that if I'm looking for the yellow duck in the yellow background, it will be impossible, right? So what do I need if I want to work with shapes? What's the difference between the right side and the left side as far as detecting the duct is concerned? No, the color of the duct is the same, or pretty much the same. No, but the big difference here is I actually have some contrast, right? I can actually extract the shape because I can actually see an outline. On the right side here, there's nothing I can see that would allow me. There could be a circle here, there could be a square, there could be a triangle. No way for me to know if there's anything. So if we're working with the shapes, then we need to have some kind of contrast for at least a large part of the shape. It's possible to detect the duct if there's only a little bit that is yellow. Like here, if now that ship is yellow, the yellow submarine from the Beatles, for example, then you would still be able to detect the duct because you can get the general outline of the other parts. And then you can sort of guess what this shape here should be. Right? But if it's all yellow, if there's no contrast, there's no way that you will be able to detect anything shape-based. So we need to have a contrast. So what does it mean as far as an image is concerned? How do I know whether I will have a contrast or not in my image that I can use in order to detect circles, squares, rubber ducks? Or, in other words, what's the big difference between these pixels here and exactly this pixel here?
Changing of color.
There will be a huge change of something, in particular in this case also color, but sometimes it's just brightness, or yeah, most of the time it's really just brightness, but it could also be the same brightness, different color, even though that doesn't really happen in natural scenes very often. It could happen in artificial scenes. So the big, in order to be, yeah.
This is a mic is now.
The mic is not open. Oh, it would be open on this one here. Let me check. Ah, yes, here I'm muted. Yes. Okay, now it should be better. Yeah, now I'm showing green here. So, what we're looking for is change, right? Between, in the neighborhood of that particular pixel, and then we can detect some outline, some shape. Then we can match that to some way we can try and figure out if this is a circle, is this a square, is this a rubber duck. So all our shape-based methods are relying on being able to extract the outline, and extracting the outline requires for us to be a difference, some change from the object of interest to the background, the parts that are not of interest. So let's continue. So I just need to wait for the machine to boot up and install my environment. So here we're loading an image. So you may have seen it before. This is a very famous movie, Casablanca, from the 1940s with Humphrey Bogart. This is some scene. So now let's see how we actually implement detecting shapes. The technical term for it, what we're calculating are convolutions, but the main point is that we can detect changes in the contrast of the image. That's why, and usually for edge detection, that's often run in grayscale, which means the first thing you do in this case is throw away all the color information and then start matching shapes. So that's why I'm starting with a grayscale image at this point. And we're introducing convolutions as a general operation of on images, pixels. And the basic idea is that we have a weight matrix that we apply to every pixel, and the values in the matrix correspond to the weights of the neighbors of that particular pixel. That becomes more clear when we actually run it. The convolution matrices are usually odd number of rows, odd number of columns. The simple reason for that is that then you have a defined center. Like convolution matrix 3 by 3 means that you look at your top left neighbor, your top neighbor, your top right neighbor, your left neighbor, your right neighbor, yourself, bottom left, bottom right, and bottom. And then you have one center pixel. If you have a 4 by 4 matrix, it's not clear where the center pixel should be applied to. Is that the one top left, above the diagonal, or below the diagonal? When we're applying the convolution, then at the edge of the image, we have to decide what we want to do. Either we pad the image, which means we just copy the columns and the rows, or we set them to 0, or we wrap around. Those are the popular choices. And depending on what your application is, one may make more sense than another. So let's start very simple with a 3 by 3 convolution matrix. Like this. And now I can assign weights to it. And this would be my center pixel. That's a pixel that I calculated the correct value for. Now I can put weights there. Now adding different weights will have different effects on the image. And that's what makes convolution so powerful, in the sense that there's many different kinds of applications that we can do with our convolution. We can have many different effects on the image visually. So the first one we want to look at is how do we find out, how do we get a convolution matrix that will return if we find a vertical edge in the image. So now I have a very simple image. Right, and maybe to make it a little bit more interesting. So if this is my image, these are white pixels, these are black pixels, and I have a convolution mask that looks like this. And is 0 everywhere else. Then what will be the impact of this particular convolution mask on this input image? So if I start adding my input image, then for the first pixel here, what I will calculate is 0 times my top neighbor, which will be this pixel here. If this is my current pixel, then my top left neighbor multiplied by 0. So it doesn't really matter what that pixel is. I ignore it. This one is ignored. This one is ignored. They're all zeros. Here I have a -1. So here, that's where we need to figure out what we want to do with the image. Let's say I extend it. So it will be also, I add an extra row here, I pad it, and we have an extra row of zeros here. So then this will be 0. 0 times the center pixel, 1 times this, which is 0, and these are all zeros. So this will return a value of 0. If I do it anywhere in this area here, so I'm looking at this pixel, and I look at top left, I apply this convolution matrix over this particular pixel, then I have 0 times 0 plus 0 times 0 plus 0 plus 0 minus 1 plus 0 plus 0 plus multiplied by 1 plus 0 times 0 plus 0 times 0 plus 0 times 0. So this pixel here will also be 0. What happens in this place? Well, here, now, let's say that all my values are 1. So I end up with 0 times 1 plus 0 times 1 plus 0 times 1 plus minus 1 times 1, which is minus 1, plus 0 times 1 plus 1 times 1 plus 0 times 1, 0 times 1, 0 times 1. So in this case, this one here will also be 0. If I apply that convolution mask to this area here, then I also end up with 0. So far, our convolution mask doesn't seem to be doing anything interesting because it returns black for a lot of the area. The only interesting part that we have would be at this location, for example. Take this one. In here, I get all zeros at the top, all zeros at the bottom, all zeros for myself, but I get -1 times 0 plus 1 times 1. So here, I actually get a response of 1. Right? So that means if I take that input image and I have this convolution mask, then my output will look something like this. It will detect this shape here, exactly, the edge, the horizontal edge. So this is the simplest kind of edge detector you can sort of think of. And in fact, it does what we said we need to do in order to be able to detect a shape, which is looking for changes in the brightness of the image. Now, instead of just looking between the previous pixel and myself, this one does it a little bit more elaborate. It actually looks at the left pixel, the left neighbor and the right neighbor, and it makes a difference between those. The reason is because we want to make this an odd numbered matrix. You can actually also run this convolution mask with just 2 entries. Actually, you could do it with just a single mask, 1, -1, +1. That will give you a similar result. So here's convolution masks. How about this convolution mask? If I now rotate it and I go -1, +1, everything else 0. Since I run this over the image, this is called a filter, convolution filter. And what would this filter be sensitive to if we have it like that? Then, to get a strong response, my input image has to look like having a +1 here, right? And has to have a 0 there. So in this case, it will be sensitive to horizontal edges, not vertical. So if my input image were to look like this, then this change in brightness, I would get a very strong response from this filter. Right? That's what we just discussed. For this part here, I would also get a strong response, but it will be this filter. Any other response I will get? Well, our filter, if we apply it, what happens if I apply it at this pixel here? Then what will be the output of this filter or that filter? Yeah, so here Right? If I look at that filter there, I'm going to get 0 multiplied by, because I'm looking at the right neighbor, so it'll be 0 multiplied by +1, which is 0, right? Minus, and then this is a 1 here. So I'll get a response of -1. So this filter, this area here is also going to get a strong response from that filter. Right? Except the sign will be different. Now, depending on your application, sometimes you care about the sign, in which case you need to keep track of it. It means different things. Sometimes you don't really care whether it's going from high to low or low to high, in which case you could take the absolute of your filter response. It really depends on what you're trying to detect. Similarly here for this filter, I also will get a strong response on the on the horizontal line, the horizontal dimension. So many different things you can do with a convolution mask, convolution filter. What will this filter do here, the 5x5 filter? If I apply that over the image, then that will actually shift the image, right? Because it doesn't care about any of the neighboring pixels. It just takes the right neighbor and will write it in here. So that means that the whole image is going to be shifted to the left. Now, when we actually run this, we have to be a little bit careful because I think I used the SciPy single function to do general convolution in 2Ds. I don't need to in case I don't need to implement it by hand, but I think the convolution mask there is actually swapped around in the x direction, so it may shift it to the left instead of the right. So here I apply this convolution mask, and the mode means same means that it extends the pixels toward with the same color. It's like there's a boundary around the image. And here I do it repeatedly 20 times, and then I can show the image parts and the actual output is. And here I have another one where we take just the top part. So yeah, the array is actually swapped when you use the convolution. I forgot exactly what the reason was for that, but there was some reason why they swapped the array coordinates. So this, if you look at the result, actually shifts it to the right, not to the left. If I wanted to shift it to the left, I would have to change the convolution mask like this. And so now it's shifted to the left. And then, of course, we can also shift it up and down. So that will shift it down now, even though you would expect it to be shifted upwards. That's because the mask is flipped when it's applied. Here, this one shifts it down. Here we shift to the left. Here we shift to the. This one should shift it to the. This over there. So shift it to the right actually shifts it. So let's have a look at some other features that we can use for with our convolution mask. So here we take the blue channel and then replace it in the image. Where the image is bigger than 200, we write 255, otherwise we return 0. So this one here does a thresholding operation on image 2 and scales it to be between 0 and 1. And then it extracts a convolution mask, which is at pixel location 175 by 550 and 71 by 71 pixels wide. And so by taking that little sub-image and then running the convolution mask over the entire image, I can find the region that best matches the sub-image. So here's my input image. This is the template that I'm looking for, which is that little red region that I extracted here. And then this is the response of my filter, which shows pretty good response there. The area that I was actually scanning. But let's pick a different coordinate to make it. So let's move it down. This is 70. Let's move it down and to the right by 100. Let's make that 275. And 650. So yeah, now we get a much stronger filter response there. The previous one on the left was a little bit too weak. It had multiple branches. But here you can see that this is exactly the shoulder that I just extracted. So that's the maximum response by the filter. So using this convolution mask, which, by the way, when you're looking at deep learning architectures nowadays, then CNN networks, that's exactly the first layer that they implement as well. Basically, you're first trying to learn a convolution mask that then is useful for doing the further processing that you want to do in your image. So CNN networks, instead of sort of doing the figuring out what weights we want for our mask by hand, we have the network try to learn the correct weights for our layers. So another advantage of this algorithm is that you can implement it very quickly on a GPU. It can run very efficiently in parallel, can be parallelized. Now, this template matching may look very simple, but I actually used it last year to good effect. Let me just see if I can see here. Not there. Okay, let's just take a 5-minute break. I need to get the link from the other computer, and then I'll show you what I did with the template matching last time. It's not on that computer, or maybe I can. Let me try and see if I can do it from here. It's too slow.